По-английски, да? Я не знаю, я вещь, которую если нет так говорить, я лучше говорю. Если равно. Кто у нас там присутствует в этом? Включился. Кто? Принц. Кто? Принц. Магнус. Какой? Принц.
То есть кто-то есть из иностранцев. Да? Ну, ладно,
So our next speaker is Professor Alexander Nikolaevich Skubachevskii, the guy of his talks.
Thank you. My lecture is devoted to some properties of well-known Vlasov equations. Last time they became very popular in mathematical physics due to important applications. These equations describe many problems in astrophysics, well known in theoretical physics, Landau damping effect, kinetics of high temperature plasma, and so on. In my lecture, I would like to consider the behavior of high temperature plasma in fusion reactor. First of all, let me mention that temperature in such reactor usually is greater than 100 million degrees. Therefore, if sufficiently large number of particles reach the boundary, a reactor could be heavily damaged or explode. In another case, if some smaller part of particles will reach the boundary, it's possible another not very good effect that it will lead to cooling of plasma and thermonuclear reactor will stop. Therefore, one of the main problems in plasma physics is the following: how to provide a confinement of plasma. This means that physicists are trying to organize control theory of plasma in such a way that plasma should be located at some distance from the walls of the reactor. And usually the main tool of investigation of rarefied plasma is closely connected with so-called Vlasov equations. In this lecture, I'll consider one of the main models of fusion reactors, so-called mirror thread. And I'll also show a picture of another model, the Tokamak. The main role in the equations plays a prior estimate of strange of self-consistent electric field with the help of initial density distribution function. Here you can see system of equations 1, 4. Unknown functions are phi of S E and F beta of S V. What do they mean? Phi is potential of self-consistent electric field at the point X at the moment E. And F beta represents here so-called density distribution function of charged particles. If beta equals to +1, this corresponds to positively charged ions. If beta equals to -1, this corresponds to negatively charged electrons. Here we have E charged electron and equation 1, this is well-known Poisson equation. However, in this equation we have 3 unknown functions: phi, f +1, f -1. This corresponds to Coulomb law. In the right-hand side, we have total density of charged particles. Vlasov equations 2 describe kinetic of charged particles. Here we have scalar problem. M beta, this is mass of beta type particle minus gradient with respect to x of phi. This is strength of self-consistent electric field. C, this is velocity of light, and this term D, this is external magnetic field. With the help of this field, physicists provide confinement of plasma. This is very important term. And this term describes so-called Problemsfor. In brackets, we have vector problem. In addition, we put initial conditions for t equal to 0 for density distribution functions, and for phi we put boundary conditions. So on the boundary we have an area of potential electricity. Long ago, it was proved that after reaching the boundary, trajectories of particles, mathematically speaking, characteristics, can lose further property with respect to initial data. Therefore, in general case, we cannot guarantee existence of so-called classical solution if we consider mixed problem. So problem not in the whole domain, in the whole space, but in some domain with boundary. But people found 2 cases in which it was possible to prove existence of global classical solutions. I mean, if our domain is half-space and the initial conditions are either Dirichlet or Neumann, I mean conditions for potential of electric field. It was proved in the papers of Gore and Juan and Vlasov. In general case, existence of classical solutions in the domain with boundary is unsolved. Since, as I mentioned, in general case, it's difficult to guarantee existence of classical solutions. It were a lot of papers devoted to existence of so-called global weak solutions. Another reason for investigations of such solution is the following. As it is known from experience, majority of numerical methods converge to weak solution. This is a very rough picture which illustrates that in reality plasma consists of particles both positive and negative, have positive and negative charges. Nevertheless, in many papers, mathematical papers, mathematicians usually consider plasma, which consists of particles of the same size. But in reality, it's not true. Therefore, in this lecture, we consider real situation, particles having two sides. This is a very rough picture of tokamak. Here we have cross section of vacuum camera. This is plasma. And in this situation, external magnetic field, here you can see lines of this field, consists of two parts, so-called colloidal field and toroidal field. Roughly speaking, colloidal field provides confinement of plasma, and toroidal field provides, in some sense, stability. In Moscow, usually physicists are constructing and are studying plasma in tokamak. By the way, this is Russian abbreviation, which means stock camera магнитная катушка. However, there are a lot of other models, and one of them, which exists already more than 50 years, this is so-called mirror trap. This magnetic trap was invented in Institute of Nuclear Physics in Novosibirsk by academician Bucher and his pupils, and now also this magnetic ring works. It has the shape of long cylinder, and in the middle part, cylindrical part, we have magnetic field which is homogeneous and has direction along the axis of cylinder. At the end, it becomes more narrow, and this is so-called open magnetic ring. So partially, more than the majority of particles due to such deformation of magnetic field can be reflected inside camera, but some of them can fly outside. Therefore, usually physicists are arranging something like chain of magnetic rings, one after another, in order to decrease the so-called end losses of particles. The difference between such traps, roughly speaking, of course, is the following: that in the first case, in tokamak, now physicists are trying to finish the most tremendous project maybe in the world in France. They are constructing so-called ITER. This is a huge building with tokamak inside. So in tokamak, time of living for plasma is about several minutes. In mirror trap, it's much less, milliseconds. Nevertheless, it's much cheaper, many thousands times cheaper. This is a real mirror trap, which is located in Bucher Institute in Novosibirsk. Here you have a chain of magnetic rings. Here we have a special camera for injection of charged particles. And from my point of view, the most interesting thing you can see here, this is small plastic bag, which contains very, very small glass, which have inside semi-nuclear fuel, deuterium. And it provides a long time during which we can get experiments in such a reactor. And of course, in the case of deuterium, we have almost no radioactivity, so it's much more safe than nuclear reactors. And this is one of the first models. Nowadays, it doesn't work, and of course, it doesn't correspond to nowadays. Not possible to organize very complicated experiments, but this is one of the first neural drugs in the world. Here you can see our notation, but I explained you before. The only thing what I would like to mention is that our domain, this is long cylinder, as in reality. G, this is bounded domain with infinity differentiable boundary, and D is sufficiently large. Here we are introducing spaces in usual manner. We denote by CK space of continuous functions which have continuous derivatives with finite norm given by the following formula. CK0 by CK0 we denote the space of k times continuous differentiable functions with compact support. CK space of vector functions in three-dimensional space with coordinates belonging to the space CK. Now we will introduce one space of functions defined with respect to t on the interval, closed interval unit large, with the variance in the space CK. We equip the space of the following form, and WEK with solid space function. Now, consequence of our steps concerning the proof of existence for weak solution is the following. As usually, first we consider some averaging of equations. Then at the next step, we prove existence of such solution corresponding to averaging problem. Then, second step, we obtain a priori estimate. This is very important, but this sounds a little bit strange for physicists because usually they don't understand what's the reason for studying some priori estimates. Of course, medically they usually, but this estimate plays an important role. And finally, we prove existence also of weak solution. So let us consider last equation 5. Kappa means coupling of averaging, and F beta kappa are solutions of two equations 5. And instead of initial problem for function phi, we shall exclude function phi using green function, but green function with averaging. We introduce the well-known function, so-called head function, by the formula X. This is a supported function, and we denote by omega kappa averaging kernel by the following formula. Then this is again infinite differentiable function, and support of this function corresponds to the total of this formula. And naturally, due to such an application, an integral of this function is equal to 0. Then we consider averaging of green function. This is green function of Dirichlet problem. We define E kappa range of self-consistent electric field by the formula. Then phi kappa, this is convolution with average green function and the density, total density of charged particles, which is given by the formulas. So what are we doing? I'll repeat once more. This is something like the step towards a system of 2 equations instead of 3 equations. But we add some relations which connect potential averaging potential of electric field with density distribution function. And this formula gives averaging green function. Together with equations 5, we consider initial condition 11, and we assume that initial density functions are continuous functions, functions with complex supports. Theorem 1. Let F0 belong to the state, and of course, we assume that functions are non-negative. Then, for A kappa, there exists a strong solution F beta kappa of system 5 with conditions A11. Now,
is the solution on the infinite interval time?
No. I told at the beginning that we consider this at arbitrary but fixed interval, 0, t large. Yes. Okay. It will be. I understand what is behind your question, but now I'm not sure that I will present everything. Therefore, you can continue after the end of my lecture, but I understand the sense. What is behind? Formally, I answer. It's important to realize the following notations. G delta, this is a set of points at the domain G lying at the distance greater than delta from the boundary. We have the same notation for full delta, but here we have distance between points F from cylindrical part of boundary. So it's easy to understand what we want to obtain in nearest future. We would like to obtain solution which supports lying at some distance from cylindrical part. And of course, if D is sufficiently large, of course, plasma also will not touch the basis of cylinder. Now, condition first. Let F beta 0 belong to C1 0, and support of F 0 beta belong to the following set. What does it mean? First, that with respect to space variables, density distribution functions belong to some ball of radius lambda. and lying at a distance greater than 2 delta from the boundary. With respect to velocities, the force belong to some ball B0. These are, these and these are usual assumptions concerning initial density distribution function. But since we consider confinement, which was not studied before, we consider, of course, density distribution functions, initial density distribution functions at initial moment, lying at some distance from the cylindrical part of life, from the wall of the reactor. Now we denote by R of T with the help of the following expression, and we assume that this R of T is less than T. Theorem 2. Let conditions 1, 2 be fulfilled. Then the following estimate is true. Well, unfortunately, I have no time to explain the proof. On the first glance, it is sufficiently clear. On the second glance, you must provide existence of so-called generalized characteristics on the whole interval below. And only in this case we can provide this estimate, which is based on existence and uniqueness of this problem in the cylinder with and estimate in the space W42 plus obviously bearing theory. But in addition, here we have not F beta, F0 beta. This is the now, condition 3. This condition means that B is sufficiently large, but it is giving this quantity, this assumption. Now, let us write original mixed problem for Vlasov equation with respect to two functions. Idea is the same. We change our Dirichlet problem for Poisson equations, in right-hand side of which we have density distribution functions, by only Vlasov equations, in which E satisfies the following relations, which were obtained with the help of green function. Here we go. Now definition 1. This is a little bit from the first glance complicated definition of weak solution. You see, instead of traditional definition of weak solution, for example, in the case of second order elliptic equations, 4 parts with the mass. I would like only to pay your attention to the main part of the definition 4. You see here, phi is so-called test function. And we are transmitting our derivatives to this function phi. You see, here we have derivative. But as for t, we cannot guarantee such a nice expression, because that function phi doesn't depend on it. And this function is not, generally speaking, is not differentiable. But when we consider integral of this product, In the case when we have all above mentioned assumptions, this integral is continuously differentiable with respect. Therefore, we can, of course, this is special result I didn't mention. Therefore, we can write this integral identity in the following form. Now, this is the main condition 4, which gives in explicit way, this is very simple inequality, assumptions for external magnetic field which provides confinement of plasma, but not simple confinement, at some distance from the boundary. So, what does it mean? The first addendum corresponds to the shape of so-called Larmor orbits, because in the case when we have external magnetic field, but no electric field, particles of rarefied plasma are moving. This is well-known fact during maybe almost 100 years plasma physics. Particles are moving up either along circles or along helices. Only two options. And if magnetic field, of course, if magnetic field is homogeneous, as we assume here. But what is interesting, if we increase strength of external magnetic field, then the radius of such orbits, either helices or circles, is decreasing. Therefore, particles which, if they started at some distance from the boundary of cylinder, cannot reach this boundary. But we have in reality self-consistent electric field. Therefore, the second addendum, which is closely connected with theorem 2 with a prior estimate, guarantees us that even if initial density distribution functions are sufficiently large, and the electric field also is sufficiently large, we can find such B, which is greater than this sum, which provides confinement of plasma. So, even we have the following situations. If we don't have electric field, then we have such one more trajectory. Particles at the initial moment is inside cylinder located at distance to delta from the boundary, then all orbit is strictly inside cylinder which is located at distance 3 delta. So we can move closer to the boundary, but this this distance it can be greater than delta 2. And what's interesting, what's interesting that if we have electric field, we have deformation of this trajectory. But even deformed trajectory cannot be cannot lie in our domain at the distance less than 3 delta R2. So even deformed trajectory will be, in this sense, nice. It doesn't matter which kind of trajectory we have, but deformation of trajectory will be not sufficiently large. Even if electric field is large, we provide it using magnetic field. And finally, we have the following case. Let conditions 1 for the fulfilled, then there is a weak solution F beta for system 13-15, which is equivalent to Vlasov Poisson system in long cylinder, such that supports belong to this set. Here this is the main part of this result. It will be at a distance not greater than 3 delta L2. And of course, balls in which we have modulus of space coordinates and velocities will be greater, but still fine. Now I would like to show you some bibliography. I have 1 minute. This is original paper of Vlasov, which was criticized by many physicists this time. They didn't understand this paper. They were definitely against such investigations, but later, due to moral support of academic Bogolyubov and some famous foreign physicists like Max Born, these equations became very popular in physics, and they became the main tool in implementation of Vlasov. So, it was a book, but the original paper was published by Vlasov in 1938. There are also some references to our papers, me and my colleagues, including young German mathematician Jürgen Kierkegaard. Mainly, they were connected with each of classical solutions, but for sufficiently small initial density distribution functions. This is solution devoted both to tokamak and mirror trap, in which we have found sufficient conditions for existence also in the explicit way of stationary solutions, which might exist for any stationary. And what's interesting that we have found the following fact. If we increase total charge, because in plasma it must be sufficiently large, the magnetic field which we use for confinement of such plasma will increase only like square root from total charge. It's growing not so fast. Also, I would like to mention very big paper concerning weak solutions of German mathematician. He was a former pupil of famous reactor. I have mentioned already paper of Bohr devoted to the existence of classical solutions for mixed problems in half case. Then also I mentioned some papers of myself devoted to plasma confinement in the case of small initial distribution functions. Again, this is paper with my Japanese young author, quantum velocities, again, is connected with confinement, not with confinement, there's no paper in this field. It was devoted to existence of classical solutions in half phase with the shear problem. Now that's all. Thank you very much for your attention and for your patience.
Есть короткий вопрос.
Речь идет о некотором поле однородном, и при этом есть ускоренные заряженные частицы. Там какие-то приближения делают, они же тоже излучают электромагнитные поля.
Ну, конечно, да, это простейшая модель. Более точная модель, которая только сейчас считается численно, и даже численные методы, более того, не обоснованы. Это нужно рассматривать уравнение Власова-Максвелла. Когда частицы излучают кроме того, магнитное поле, и есть не только самосогласованное электрическое поле, мы берем по существу из системы уравнений Максвелла одно уравнение, вот это уравнение Poisson, которое описывает потенциал электрического поля. А надо еще добавлять 3 уравнения. Тогда, значит, мы можем учитывать этот эффект. Качественно это не исследовалось. Но, естественно, это в плане есть. Что я могу сказать еще в качестве, как говорится, приложений? Когда мы обсуждали мой доклад еще несколько лет назад в Новосибирске, когда Галина Геннадьевна Лазарева, которую я пригласил к нам в институт, она приняла это приглашение, она уже несколько лет штатный профессор математического института РУДН, она как раз очень известный специалист в области вычислений численных поведения кинетики высокотемпературных плазм, в том числе удержания. И вот у нее было такое предложение, которое сейчас мы вот как раз реализуем, использовать ряд этих результатов как тестовый пример. Что это означает? Я повторяю, современные численные методы, к сожалению, в большинстве случаев не обоснованы. Их применение основано только на гигантском опыте людей, которые считают, и которые хорошо знают доказательства базовых классических методов. Но тем не менее, когда нет доказательств, что-то приходится как-то аргументировать. Для этого создаются тестовые примеры. Они состоят обычно в нахождении частных решений и сравнений, что компьютер даст в случае модели, и что мы имеем здесь. Здесь это настолько сложная система, что частные решения тоже не найдут. Но зато есть оценки. Вот посмотрите, на чем основана наша вот идея. Есть оценка, когда должно быть удержание. Происходит счет. Есть на каком-то шаге, а мы знаем, что на интервале, там, предположим, там, сколько-то там секунд или там, минут или часов, мы должны иметь удержание плазмы, а на самом деле частицы вываливаются в результате численного счета по границе. Это неправильно. Понимаете, вот этот тестовый пример основан на другом принципе. Сейчас мы работаем в том числе на моделировании. То, что, так сказать, является, значит, конечно, хотелось бы перейти и к уравнению максимума, но даже вот эти классы идут очень долго. То есть обычно математики пишут, основной мотивацией наших исследований вот этого является исследование высокотемпературной плазмы в термоядерных реакторах, но основная задача — это удержание и доказательство теоремы существования. Понимаете? То есть решения нужны, но не такие. Решения нужны, которые строго внутри. Это вот постановка, которая вызвана физическим смыслом. В этом, наверное, смысл доклада. Спасибо.
У меня есть вопрос, но у нас времени нет.
Так, я возвращаюсь.
Сейчас через